and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 21 in the series on Chapter 4.6, Polynomial Inequalities. Before we begin, I'd like to just give a general overview of the procedure. When we're given a polynomial, we can, in general, set it equal to 0 by grouping like terms on either side. Once an inequality looks like this, we're really just deciding whether or not something is negative or positive, depending on what the question is asking. For example, if our question wanted us to find where is a polynomial positive, if these were positions A, B, and C, then this would happen precisely between A and B and from C onward. We're going to want to use brackets whenever we're using inclusive inequalities. And conversely, if we were asked the question, where is such a thing negative, using a strict inequality, well, this would be from negative infinity up to A, not including A, and also between B and C, but not including B and C, because at those points we are actually equal. So with equalities, we include the endpoints and use brackets. If it's strict inequality, we will not include the endpoints and use parentheses. But one thing should be clear from this picture, and that's how important these zeros were to deciding where the polynomial could go from being positive to negative. Since polynomials are continuous, they can only change sign by passing through a 0. And that will happen, it'll cross through a 0 when the factor corresponding to that root has odd multiplicity. We saw before how they'll bounce off that 0 if it has even multiplicity. So now let's go through the guided notes. This polynomial is already factored, and each term has multiplicity 1. So first, I would mark this minus 7 and this positive 8 as being the important points to note. Then we're going to want to figure out if it's positive or negative in these regions. We can do that a couple different ways. Number one is we can use a test point. For example, if I plug in 0 into this expression, I'm going to get negative 56. And so we know actually everything in this region is negative. If this one's negative and it doesn't change sign until here, then so must everything else in this interval be negative. Now, as we said, these have odd multiplicity. So we are crossing the 0 and changing sign at those points. So we then know about these two positives. You could plug in a test point from every region, but in general, if you know the multiplicity, this is much faster. Another thing that we could do to generate these positives and negatives is we could take a look at this inequality and say, well, if I expand that, that's going to be x squared plus some lower order terms. This is a positive quadratic, and it's got these two zeros. So we know it's going to have this shape. And that automatically tells us where it's positive and negative. So even just a quick sketch like this can sometimes help us see exactly where it's going to be positive or negative. Now, the question is, where do we shade and what is the correct answer? That's going to depend on what the inequality actually says. So this is greater than or equal to 0. So we are going to shade where it is positive, and we are going to include the endpoints because this is inclusive inequality. That gives us the following two intervals, which we stitch together with a union symbol. Another thing that we could do is use a graphing utility. Here I've used Desmos to graph some of the equations, and we can see that it has this upward facing parabola kind of a shape with two roots, which really tells us everything we need to know. Here, however, are those two roots at positive 8 and negative 7. And we could even ask about where the inequality is true. And this would tell us precisely where to shade, although we can also see this is positive in this region and positive in this region. For the next one, we want to do the same thing. We want to factor this. I'm going to factor out a negative x, just to make this one easier to look at. And then we'll see this is going to be x minus 2.5, which gives us 0 and 2.5 as roots. So we want to mark those on the number line with closed circles, because this is inclusive inequality. And then we could use a test point to calculate whether or not it's positive or negative in this region. Here I've chosen 5 and plugged that in. And it tells me that we are indeed negative times positive, so negative in that region. And so I mark this as negative. And it has odd multiplicity on each one of these roots, so it changes sign after each root. We're looking for where it's positive, so I'm going to shade where the plus is. And that gives me the following interval. Alternatively, we could have just noted that this is a downward-facing parabola and it has two distinct roots, and so it must look like this, and therefore it must have negative to negative as its distribution of signs. Here's what that parabola would look like graphed, and this region is where it would be greater than 0. So given that we will also include these endpoints, this shows us our interval. To figure out the zeros of a polynomial, we're first going to factor, and that's going to tell me that I have distinct roots at 9 and 2. So I'm going to put dots at 9 and 2, and I'm going to make them closed dots because this is a inclusive inequality. We also know this is an upward-facing parabola, so just drawing a quick sketch, we would know what the sign distribution was, but we could use test points, plugging in a 0 here. Well, let's even just look at the first equation. If I plug in 0, I get 18, which is indeed positive. So we know the distribution of signs will be positive, negative, positive by either of these two ways, test points or a quick sketch of the graph. Finally, we could decide where to shade based on this equality. It's a greater than 0, so we're going to shade where it's positive. This gives me the following two intervals, which we stitch together with a union symbol. Let's take a look at how we can use a calculator to help us, just in case you don't have access to Desmos, but you are allowed to use a TI-83 or 84. You can plug this equation into your y equals input. Looking at the graph, we can see it has the following shape. Now, this actually gives us enough information, I think, but we really would like to confirm that this thing has the roots that we found by factoring. And there is a command to find out where a graph is equal to 0. If I go to second calc down to 0, we can use the 0 finder on the calculator. We just have to give it a left and right boundary. So I'm going to get just to the left of, let's say, the 0 here. That marks a window for it to look for a 0. So we go to the left and right of the 0, and then we get close to the 0 and press enter again, and it does indeed confirm that we have a 0 at 9. It's inclusive inequality, so we include these endpoints, and we shade where it's positive to get these two intervals. Okay, here's another one. I prefer to factor a polynomial with a leading term that's positive. It helps figure out the signs a little bit more easily. So what I'm going to do is take the first line, I'm going to multiply on both sides by -1 to make that change all the signs of the coefficients. But I also have to flip the direction of the inequality. We're still using all the rules that we normally use for solving inequalities, and that includes if you multiply or divide by a negative on either side of the inequality, you're going to have to flip the direction of the inequality. So once we factor this, we get x minus 2 and x plus 1. We put dots there, closed dots, because this is inclusive inequality. And then we could use a variety of methods to figure out what the pluses and minuses should be. I'm talking about this inequality I derived now, which is going to be a upward-facing parabola with two distinct roots. So we would know the positives and negatives are distributed thus. We could also take 0 and plug that in to find -2 times 1, which would give me a negative. And we have odd multiplicity roots, so we know it changes sign across the roots. Where are we going to shade? Well, this one is asking us, where is it positive? So we shade precisely where there are pluses. We could also look at this parabola. Here's the original parabola with the negative leading term. And the original question was, where is it negative? And notice that's going to be precisely in these two regions, which is what we found out by flipping the direction and asking where it was positive. We still got precisely those two regions. So we really were solving the same two questions when we flipped the direction of the inequality and changed all the signs. For number 5, when we go to try to factor this, we're not going to have an easy time of things. And that is because, checking the discriminant b squared minus 4ac, we're going to get a negative under that radical in the quadratic equation. This tells us that the x values that would make this 0 are complex. In other words, there's no real solution that's going to make that 0. There is no x-intercept. So when that's true, either your parabola is going to look like this, or it's going to look like this. It's not going to hit the x-intercept. And we know it's an upward-facing parabola because this leading term is positive. So then we could ask the question, where is that thing negative? Well, never. It's never negative. Taking a slightly nicer look at that graph, we see that we have this positive quadratic, positive upward-facing parabola, and it is never below 0. So nothing gets shaded here. Notice, though, that if I were to ask where is it greater than 0, well, that would shade everything. This would be the whole real number line. So one of those two situations is going to be what happens if you wind up with parabolas with complex roots. The next one goes similarly. If we tried to factor this, we would stall out and we would check to see, well, what is the discriminant? Is it going to be irrational, or is it going to be complex, or both? And we would find that the discriminant is negative. So the part of the quadratic equation with a square root would have a negative under it, and that makes the answer complex. This is a downward facing parabola that never hits the x-intercept. So we're going to have something that looks like this. It is in fact always negative. And so when we ask this question, where is it negative, the answer has to be the whole real number line. Here's a slightly more accurate graph of that quadratic, and asking the question, where is it less than 0, is, well, everywhere. It shades the entire thing because this is always negative. Here we have an interesting one because we finally have a root with even multiplicity. This is a perfect square trinomial, and once you write it in the correct order and factor, you get x plus 5 squared. And we're asking, where is this less than or equal to 0? Well, it's never less than 0, but it is equal to 0 at -5. And then it bounces off that and goes in the other direction. So we really want to just shade the -5. We could write that in set theory this way. They're asking for the answer in interval notation, which we can do. We can write a single point for an interval. We just have to kind of use this degenerate interval where these two endpoints are not distinct, but we use a bracket to include them. So this kind of says, go from -5 and including -5 up to -5 and include -5. So it just gives you -5. That's all that's in this interval, is that single point. And that's all that we would shade. For this next one, it's already set equal to 0. So we'd like to try to factor it. Using the AC method, we can factor it like this. And that gives us roots at -2 and +5/4. So we're going to mark those on the graph with open circles because this is exclusive inequality. Then we want to know where the pluses and minuses should go. Well, this is a positive leading term, and so we're going to have an upward-facing parabola with two distinct roots. That lets us know it's positive, negative, then positive. Alternatively, we could plug in 0 into this equation and find out that we had a negative in that region. We'd have 2 times -5, that would give us -10. So it's going to be negative in this region, and these are odd multiplicity roots, so it changes sign around these endpoints. So the question's asking, where is it positive? That means we're going to shade where the pluses are, and that's going to give us the following two intervals that we stitch together with a union symbol. The next one proceeds similarly. I would take the first step to get rid of the common GCF of 3 that's in each one and write them in the correct order. Then you're going to see that it factors as x minus 4 times x minus 2. Now, what are the distribution of signs here? Well, this is a positive parabola with two distinct roots. So it's facing upward and it hits the x-axis twice. That lets us know it is positive, negative, positive. We could alternatively plug in a 0 here and find negative, negative, which gives us positive. And that tells us, because these are odd multiplicity roots and it changes sign across each endpoint, that's going to tell us positive, negative, positive as well. So either of those two methods, test points or graphs, are perfectly fine for figuring out the distribution of signs. Now, where should I shade? That depends on the inequality. They're asking for where is it less than 0 here. So we're going to shade where it's negative, and that's going to give us this interval, and we use open parentheses to indicate that we're not including those endpoints. For this next one, the first thing I would do is get rid of the common factor of 2 that's in everything, and then I would shift these all to one side to set it equal to 0. Factoring, we get the following two factors, which tell me that we need to look at the endpoints of -7 and -2. So it's an inclusive inequality, so we could just go ahead and shade those in with filled in circles. And then we want to know about the distribution of signs. Well, again, this is a positive leading term, which means it's an upward facing parabola with two distinct roots. So it's going to go from positive to negative and then back up to positive again. The question is asking for, where is it positive? So we're going to shade where we see pluses, and that's going to give us these two intervals here. Put them together with the union symbol, and that's all she wrote. For this next one, we're going to want to do the same thing. We're going to want to bring everything to one side to set it equal to 0, and then we're going to want to factor. We could factor using the AC method. I put a 2 in each spot. I fix my signs. I put a 1/2 out front for balance. I take 2 times 15 and I multiply them together to get 30, and I look through this list to find a difference of the middle term, which is 7. That's at 10 and 3, so we put in a 10 and a 3. Then all we need to do is reduce, and we have our fully factored polynomial. This tells me that I have roots at 5 and at -3/2. So if it's an inclusive inequality, we want to put filled in dots there, and then we want to figure out the distribution of signs. This should be a positive here, because this is an upward-facing parabola with 2 distinct roots. So it's going to have the following distribution of signs. Alternatively, we could plug in 0 as a test point, and this would right here give me -15, which is negative. And we're asking where is it positive, so we're only going to shade at the positive regions here, and that gives us the following 2 intervals. Problem 12 starts to get us into the cubics. Notice that if I multiplied the first terms together here, I'd wind up with -2x to the third. So this is going to look overall like a cubic, and it has 3 distinct roots. What we're going to want to do is either A, sketch a cubic with negative leading sign, which is going to rise on this side and fall on this side, and then its 3 distinct roots are going to be seen by where it hits the x-axis here. Notice that that means that it has to be positive, negative, as its distribution of signs. Alternatively, we could plug in a 0 to see what the distribution of signs is. Here, that would give me a minus times a minus times a minus times a plus, which is overall negative, and so this region is negative. Now, these are odd multiplicity zeros here, so that's going to tell us that it's going to change sign around each endpoint. We don't include those endpoints. This is exclusive inequality, so we put open circles there, and we're asking where is it positive, so we shade where it's positive. This gives me the following 2 intervals, which we can stitch together with the union symbol. Notice it's exclusive inequality, so we want to make sure we're using parentheses. We could take a look at a graph to sort of understand what's going on here. Here is that cubic. It's kind of hard to see, right? It's very steep. Remember, you can always change your window size to see a little bit more of what's going on. We can at least see where it's positive, negative on this graph. We can also take a look at this inequality, which shades those regions appropriately. So let's take a look at this next one. We have a question asking us where this polynomial is less than another polynomial. And what we could do is group everything to one side and instead ask where this combined polynomial is greater than 0. Factoring, we get the following 3 factors, and we could figure out what our distribution of signs should look like by noting that this is a positive cubic, so it's going to fall on the left and rise on the right, and that it has 3 distinct roots. That tells me the distribution must be negative, positive. Alternatively, we can also plug in a test point. Let's say I plugged in 10, or even better, 10,000. It doesn't really matter what the value is. It only matters that it's in this region. And if I imagine something very big and positive here, here, and here, then all 3 of these terms are positive, and we wind up with a positive value. The fact that they're odd multiplicity means we switch sign at each point, and that also fills out our signs. Now we're asking where is it positive, so we're going to shade where this thing indicates a positive, and we're going to use brackets to include the endpoints. So I wanted to show you exactly how the new polynomial with everything moved to one side relates to the original question. So the original question gave us this x cubed and this parabola, and it says, where is that cube less than the parabola? Well, in between these 2 regions. Now, how does that relate to the question that we were asked about this term? We translated this to a question where we asked about where that term was positive. And we can see that it actually finds where the original cubic is less than the parabola by looking at this new cubic equation. Notice also that we find there is another hidden intercept down here where they crisscross again, and the cubic goes back to being underneath the parabola, which is hard to see on the graph. But it's pretty easy to see on the graph of this new cubic, because now we're just checking to see where is it positive or negative. So we're solving sort of a new question here, but that new question will have the same answers as the original question. Okay, moving on. We don't have to make the leading term negative to positive. We can just factor it out and leave it on that side. We are just going to have to be careful when we plug in our test points. Now, notice how this factors. We could factor by grouping, by taking out x squared from the first half and minus 4 from the second. That gives us an x plus 3 in 2 spots, so we factor it all the way out. This is an x squared minus 4. That's the difference of 2 squares, so you get x plus 2, x minus 2, and x plus 3 for your factors. This is a negative cubic with 3 distinct roots, so we know the end behavior is here and here. We know that it crosses 3 times, and there you have it. There's a quick graph that tells you plus, minus, plus, minus. Alternatively, you could plug in 0 as a test point, and this would tell you negative, positive, negative, positive. That's overall positive. So we could confirm that it is positive in this region with 0. It has odd multiplicity roots, and so it's going to change sign around each endpoint. The question is asking for, where is it negative? Where is it negative? So we're going to want to shade in those regions where we have a negative sign, and we're going to mark those intervals this way. For the next one, it's already set equal to 0, so we factor using factoring by grouping and the difference of 2 squares. That gets me these 3 distinct roots. We know the leading coefficient is positive, and it's a cubic, so it has this end behavior of falling on the left and rising on the right. It has 3 distinct roots, and connecting those dots, we wind up with the following distribution of signs: negative, positive, negative, positive. Alternatively, you could plug in 0 as a test point and find that this is a positive times a negative times a positive, which is overall negative. They have odd multiplicity roots all, and so that changes sign across each endpoint. We're talking about inclusive inequality here, so we include these with a filled-in circle, and we use brackets to mark the endpoints in our interval notation. Here we have one where we're given a graph, and we can use that to solve a variety of inequalities. This inequality truly relates to this polynomial, because if I bring this over to the other side, I get precisely that polynomial is less than or equal to 0. So this one will have solutions. Where is this line less than this parabola? Precisely when this parabola is less than 0. That's going to be in these 2 regions. And we use open circles for our endpoints because this is strict inequality. This goes negative, positive, negative. We're asking for where is it negative, so we shade in those 2 regions on the side, and that gives us this in interval notation. This is a similar question, but now we don't even have to move it around to answer the inequality. They're just asking, where is this function greater than 0? Okay, between these 2 regions and after this. So we're going to have from negative 4 to 2 and from 4 to infinity. And we use brackets to include the endpoints because this is an or equal to inequality. And we shade our graph this way. Last but not least, we have this kind of funny one. Finally, we have an even multiplicity 0. And so what we're going to see is this graph pass through the odd multiplicity at negative 6, rise up and bump against this even multiplicity 0 at negative 2, and then fall again. So notice it doesn't have another region where it's plus. It goes from plus to minus, equal to 0, but never plus, and then back to minus again. And so we do want to include this point of where it is equal to 0 because this is inclusive inequality. It includes the question of where is it equal to 0. It's equal to 0 at minus 2, and it's less than 0 from negative 6 to negative infinity. So we're going to want to shade these regions, and we're going to put a dot on the minus 2. And how do we write this in interval notation? Well, the same way that we did for a single point, we can use brackets and this degenerate interval to show that point. And we're going to want to union these 2 things together so you know we're saying both these things pass the test of where is this first polynomial greater than or equal to 0. I wanted to just give one additional question about this kind of thing where it bounces off at 0. What about not strict inequality? What do we do then? What if I said, where is it less than 0, but we have these 2 regions that are stitched together with this or equal to part here? Well, this doesn't count equality. You're going to have to leave that out. And so what we would have in that case, if we were asking for where is it strictly negative, it would be between negative 6 and 2 and after 2, but not at negative 6 and not at 2. So we would have to leave those out the same way that we excise points when we're dividing by zeros. We would have to leave out the 2 with this collection of symbols. All right, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies, and I'll see you in the next one.